Ever wondered why some objects float while others sink? What may be the reason for the objects to float? What causes the objects to sink to the bottom? Why some objects look suspended and easily flow with liquid, and some objects, however hard you try to make them sink, they still manage to reach the top and keep floating. Behind such wonderful phenomenon, there are well-defined physics laws. These physics laws and concepts are not just about whether something floats or sinks. They are fundamental to how our world works, from the way ships sail to how submarines navigate. Today we shall dive deep into this interesting subject of physics, that is density and buoyancy. Let us start with basics. Imagine you have two objects, both the same size but made of different materials. One feels much heavier than the other. That is because they have different densities. Density is simply how much mass is packed into a given volume. Mathematically, we can express density as mass per unit volume. Density is typically measured in kilograms per cubic meter or grams per cubic centimeter. Whether the object floats or sinks is decided by the density of the object. To make comparison easier, we use the concept of relative density, which is also called specific gravity. Specific gravity is the ratio of the density of a substance to the density of water. As an example, the relative density of a typical egg is 1.06, slightly denser than normal water. So when egg is carefully dropped in water, it settles at the bottom. Now you add table salt to make water more saline. The density of saline water is in the range of 1.11 to 1.17, depending upon how much salt is dissolved in, and is more than that of egg. So the egg rises up and starts floating at the surface. The density of the object is not the same as the density of the material it is made of. Consider two identically looking objects. Both are made of steel, but one is solid and the other is hollow. The solid object is heavier than hollow one. Naturally, the density of the solid object is greater than that of the hollow object. The density of the ship is much lesser than that of water and is not the same as the density of the steel it is made of. So the ship is able to float on water. Now let us understand buoyancy. Have you ever noticed how you feel lighter in a swimming pool? That is buoyancy in action. Let us see how physics explains this phenomenon. Consider an object immersed in a liquid. It will experience force normal to its surface from all directions due to liquid pressure, and it is the fundamental property of the liquid. The horizontal forces cancel out. The bottom half of the object experiences a net upward force, and the upper half of the object experiences a net downward force, as shown in the diagram. Note that the liquid pressure increases with its depth and follows the physics law pressure equal to rho g h. Higher the depth of the liquid, higher the pressure. As a result, the object will experience a net upward force. Buoyancy is this net upward force exerted by a liquid on an object immersed in it. What is Archimedes' principle? Any object, wholly or partially immersed in a fluid, is buoyed up by a force equal to the weight of the fluid displaced by the object. In simpler terms, when you place an object in water, it pushes some water out of the way. The weight of the displaced water creates an upward force on the object. This upward force is called buoyant force. Why do objects float or sink? Whether the object floats or sinks depends on the balance between the buoyant force and the weight of the object. There are three scenarios. If the buoyant force is greater than the weight of the object floats at the surface. Think of a piece of wood. If the weight of the object is greater than the buoyant force, the object sinks, for example, a steel ball in water. If the object's weight equals the buoyant force but it is fully submerged, it stays in equilibrium like a fish in water. How to find the magnitude of buoyant force? The buoyant force is equal to the net upward force experienced by the object when immersed in water. As you can see in the diagram, for the sake of simplicity for calculation, we just considered a small cylindrical object. The same principle is applicable to any object of any shape. Mathematically, the buoyant force is equal to the density of liquid multiplied by volume of the object multiplied by acceleration due to gravity. The density of the object and that of the liquid ultimately decide whether the object floats or sinks or gets suspended in liquid. A good example is a submarine and how it adjusts its density. The submarine takes in water to submerge by increasing its overall density, whereas it expels water with air to rise by lowering its overall density. Let us see how to calculate the density of nearly geometric objects. As an example, consider a hollow steel ball with external radius capital R and internal radius small r. The hollow portion is filled with air and its weight can be neglected compared to the portion of the ball that is made of steel. To calculate the density, find out the mass of the object, its volume, and divide mass by volume. For this example, the formula is given in the diagram. The same principle can be applied to other geometric objects. For asymmetric objects, you can follow the indirect method. Use a weighing scale to get the mass of the object, then gradually drop the object such that it is fully immersed in water and find the volume of the displaced water. Divide the mass by volume to get the density of the asymmetric object. When an object floats on a liquid, it aligns itself in a stable position. Let us explore what factors decide stable position of objects while floating on a liquid. The stable position of an object floating on water depends on the interplay between buoyancy and gravity. If the center of gravity is too high, the object is more likely to tip or wobble and may not achieve a stable position. For the object to be stable, the center of buoyancy must adjust itself to align vertically below the center of gravity. A larger metacentric height means greater stability because small tilts will restore the object to its original position. You can observe stable position of some regular geometric objects while floating on water or liquid. Here you can see a steel ball floating on mercury. The density of steel ball is much higher than that of water, but it is lower compared to that of liquid mercury. As a result, steel ball floats on mercury. Now we shall discuss about the title question, how many people Coracle can carry safely. We shall attempt to solve this question mathematically using physics laws and Archimedes principle. To analyze this problem, we shall assume that the Coracle is bowl-shaped with radius r and height h. The weight distribution is assumed to be even across the Coracle. The height of the submerged part h is calculated to ensure safety and prevent water from spilling in. The volume V of the Coracle, which is in the form of a spherical bowl, is approximated to pi s squared by 3 whole multiplied by 3 times r minus h. According to Archimedes' principle, buoyant force is equal to the weight of the water displaced by the submerged part of the Coracle. So the buoyant force is equal to density of water multiplied by acceleration due to gravity multiplied by volume. The total weight carried by the Coracle is equal to number of people it can carry multiplied by average weight of the person plus weight of the Coracle itself. For the Coracle to sail safely, the buoyant force must be greater than the total weight on the Coracle. Substituting the values and rearranging the equation, we get the equation for number of people the Coracle can carry safely. We shall take a practical example. We shall assume that the radius of the Coracle equal to 2 meters, height of the Coracle equal to 1 meter, nominal weight of the Coracle equal to 50 kg, and average weight of a person equal to 70 kg. Substituting these values in the equation, number of people the Coracle can carry equal to 74. We understand that space is not adequate to accommodate 74 people on Coracle. The theoretical result tells us the maximum weight capacity the Coracle can support without sinking. Considering highest safety standards and realistic situations like waves and waterborne disturbances, it is practical to consider 10 to 15% of theoretical weight limit, so this Coracle can safely carry 7 to 10 people. Hope you enjoyed this video. Thank you for watching and please subscribe for more educational content.